We're going to talk about what happens when something is rotating and translating at the same time. Here you can see the same disk in two different situations. On the left-hand side, you can see the velocity arrows drawn pointing around the disk because it's rotating, it's spinning around in place. At the center, there's no velocity arrow because it's not moving there. It's pinned in that location and it's rotating around it. On the right-hand side, all the velocity arrows are drawn in the same direction, so the disk is translating. It's moving left to right. We're going to see what happens when something is both translating and rotating, both motions happening at the same time. Let's take a look at a rotating disk that's translating with a fairly small velocity. For this video, we'll take the positive x direction to the right and positive rotation to be clockwise. If we superimpose the images, we can get both sets of velocity arrows on top of each other. We can add those vectors together, and we see the results here. The bottom of the disk moves slowly to the left, while its center of mass moves to the right. If we increase the velocity, and then add the vectors together, we can see that we get a slightly different result. Now the bottom of the disk is moving in the same direction as the disk as a whole. If we pick just the right value for the velocity of the disk, so that it's not moving too fast or too slow, where the velocity is exactly equal to the radius of the disk times its angular velocity, we get this result. You can see that while the center of mass of the disk is moving forward, the bottom of the disk isn't moving at all. This is exactly the condition that we want for rolling without slipping. The bottom of our disk doesn't slide forward, it doesn't slide backward, it just touches the surface and then picks back up. V equals r omega is the constraint for rolling without slipping, and that's how we found it.